Welcome to our second video for our flipped classroom in Algebra 2. I hope you survived the first day. If you found it frustrating at all, I promise it's going to get better. Hang tough, and hopefully you've got a great group of friends to kind of fall back on to kind of get you kick-started here this first week. So I brought in one of my favorite icons here, my calculator icon, just to remind you that we are going to need it throughout the video, so have it handy. If you don't have it, run downstairs, grab it really quick, and bring back. Now, what I'm going to use for my demonstration purposes is I'm going to use the TI-84 plus C Silver Edition, but by golly, if you have any member of the TI family, we're going to make it work. I do think an 84 is going to make your life a lot easier than an 83 though. So let's jump into our first definition. Tonight we're going to focus on algebraic expressions. So we'll get this title in our notebook along with the date. And let's go ahead and rip off our first definition. It's a combination of constants and variables. Alright, now you know what variables are, but do we know what constants are? Alright, so let's clarify that. What in the world is a constant? Now, a constant is basically just a simple number. If I was to give you the algebraic expression x squared minus 5x plus 10, the very last term is considered your constant because no matter what value you substitute for x, that last term is going to constantly be 10 no matter what. Okay? Using typical operations of addition, subtraction, multiplication, and division, along with sometimes what we'll use exponents or powers, or the inverses of those, which would be roots, like square root, cubed root, those types of things. We're going to jump in our time machine and zoom back to middle school really quick here. Order of operations, we're going to use an acronym, PEMDAS. And of course that stands for, we want to evaluate anything in parentheses first, and then we'll evaluate our exponents, and then we'll do multiplication and division from left to right, and last but not least we'll do addition and subtraction from left to right. Generally we work from the inside out. That's a general rule of thumb that will work 90% of the time. Generally we're going to work from the inside to outside. Okay, so here's a couple of expressions, and they're saying evaluate for x equals -2, and evaluate is just another way of saying substitute, and then we're going to just do some fun number crunching. And I'm a big fan of using parentheses here, and I think that's going to bail us out a lot of times. If I could spell it correctly here, parentheses. Okay, so let's go ahead and we'll substitute a -2. And I'm going to evaluate this by hand first, and then we can always check it on the calculator. Now remember, our order of operations says I'm going to do the exponent right here, and so that's going to give me 5 times 4. And let's see, then while I'm doing that, I can go ahead and do this multiplication here and get that out of the way. Does everybody agree with me that this needs to be a +4 right here? Because when you squared this -2, we're saying -2 multiplied by itself, so you actually had 2 negatives there to make a +4. Let's see, that's going to turn out to be 20 plus 4 plus 10. I got a final answer of 34 for my value right there. Alright, now my second one's going to be significantly uglier, so hopefully we can battle through this one. I'm going to move the screen a little bit. And I'm going to go ahead and I'm going to use great parentheses, and I'm going to go ahead and substitute my -2 here. We've got these absolute value signs, we've got radicals, we've got a cubed for our power there. We've got just a lot of crazy things happening, and let's see if we can dissect what order we want to do these in. So for me, it's all about cleaning up everything underneath this radical first. So you can treat this like, when we said PEMDAS and we're going to do parentheses first, there's really like an invisible set of parentheses around everything in that radical. So let's go ahead and clean that up. I'm getting, by the time I multiply -4 times -2, that turns into a +8. So I've really got 1 plus 8 underneath that radical, which is going to give me a 9. And now I'm going to tackle this cube right here, which means -2 times -2 times -2. And then we're being divided by 22. If I multiply all these -2's together, you know what I'm getting? I'm getting -8 right there. So let's update this. The square root of 9 turns out to be a 3. I've got my minus sign, and then I got a -8. And then I call this a double barrel negative. So whenever we have two consecutive negatives, they simply turn into plus signs. So I've got 11 over 22 with the absolute values attached. I'm going to simplify 11 divided by 32. That turns out to be 1/2, and the absolute value of 1/2 is simply 1/2. Now, if that last problem gave you a monster headache, you're not alone. So we're going to talk about how to do that on the calculator and maybe make our life just a little bit easier. So my question to you is, we're going to ask ourselves, is our TI-84 updated? And we're going to answer that really quick here. First thing I want you to do is I want you to hit the alpha button right here. And what that's going to do is that's going to activate anything that's in a light green color on my calculator. And I want you to hit F2 up here, or the window button. And if your calculator is updated, you're going to see a screen that looks just like this, hopefully. Now, if it's not updated, it's not the end of the world. We can link our calculators up tomorrow during class, and it takes about 5 minutes to totally update your calculator, and you'll be able to have the same shortcuts that I have. But what I want you to do right now is hit enter here on number 1 so that you get these absolute value signs to show up on your screen. After you get the absolute values on there, I want you to hit alpha F1 this time. And now I want you to hit choice number 1. Now the N stands for numerator and the D stands for denominator. And what that's going to do is it's going to give you the fraction bar. From there, you could start to type in the problem that we just did using special parentheses around the -2. When you're done with this radical right here, you can hit the right arrow, and what that's going to do is that'll exit the radical for you, and then you can start to type in the rest of the numerator. When you're done with the exponent of 3, you can hit the down arrow a couple of times, and that'll put you down here where you can type in the 22. Once you hit enter, you should get the same answer that we got when we evaluated it by hand. So being able to think about our order of operations, I want you to just pick a random number that we might substitute for x. Maybe we were going to substitute, we'll say a 5 for x. But without actually doing it, I want to know, can you tell me what you would do first and what you would do last without actually plugging the number in? If I did plug the 5 in, what I would do is I would end up doing everything right here first, the squared. So I would square the x first. Now, as far as what would I do last, so you kind of have to fast forward. Think about, what would you do second, third, fourth, and then eventually do last. For me, the very last thing that would happen would be this radical sign, or the square root. Because what's going to happen is, after I square my x right here, I'm going to then multiply it by 6. I'm also going to multiply my x by -4, combine these two terms together. Then I'll have 16 divided by my denominator, and once I'm done dividing, the very last thing I'm going to do is take that square root. Okay, we're going to sneak one more definition into our notebooks tonight. A rational function is the quotient of two polynomials. Okay, it's the quotient of two polynomials. Now, a rational function just happens to be a special family within the larger family of algebraic expressions. So visually, if we were thinking, all right, this circle represents every algebraic expression ever invented in the history of math. Well, within that family is a subfamily called rational functions. I'll abbreviate there a little bit. So in other words, every rational function is an algebraic expression, but not every algebraic expression is a rational function, so it's only really a one-way street. But here's what we're going to do. They want me to just evaluate at x equals 6. We're going to try to do this by hand, and then, of course, we can check it on our calculator by using alpha F1 now that we know how to do that. So again, notice the parentheses that I'm using. I think if we can build good habits for the future, we're going to be in great shape. If I clean up my numerator, let's see here, I'm getting 30 minus 2, which is really 28. If I clean up my denominator, I'm getting 43 minus 36, which I believe is a 7. Then, of course, that cleans up to 4. Now, this is worth noting. If I was to put a square root on this, it's no longer considered a rational function because anything with a radical on it's not a pure polynomial. Polynomials are terms that have just whole numbers for exponents where there's no radicals or anything ugly like that associated with them. This is one of my favorite questions of the year right here, and I think it's going to be the foundation for a lot of things we do from now till June. What does it mean to say that two algebraic expressions are equivalent? The word equivalence is absolutely one of my favorite words. So here's how we're going to go about it. We're going to say if you could substitute any value for x into both expressions. All right, so again, you're picking any value. It's your favorite number. It could be x equals 4. It could be x equals 1,000, x equals negative 23, whatever number floats your boat. And you're guaranteed to get the same answer for both expressions. Same answer for both expressions. That's what it means to be equivalent. And it's not going to work for just one value of x, but it will work for any value of x. Okay, so we're going to talk about how we're going to either prove or disprove that two algebraic expressions are equivalent. Now, disproves are my favorite because when you disprove something, you only need one example. All right. Once you've disproved it for one value of x, it's case closed. Now, for us tonight, we're going to define a prove as using 3 substitutions. And then at that point, we'll say good enough for tonight. Down the road, we're going to expound on that idea of a proof quite a bit more, but 3 will get us by tonight. So let's jump into our first example. Can we prove whether this expression here is equivalent to the one to its right? So here's what I'm going to do. I'm trying to think. My favorite number is, I used to wear number 6 in high school when I played baseball. So I'm going to go ahead and I'm going to substitute a 6 for x. First expression, 100 minus 6 squared. Let's see. I'm going to do a little mental math here. Radical 100 minus 36. That turns out to be radical, is that 64, which turns out to be an 8. Okay, so that's my first answer. Now the question is, I'm going to substitute a 6 into my second equation here. Do I get the same answer? No. So what we've done right now is we've disproved the idea that these two expressions are equivalent. All right, so I'm going to put a little line through them saying they're not equivalent. Let's try the same game here on these next two sets of equations. I'll stick with the same number. I'm going to start with, I'm going to substitute, get this bear under control here. I'm going to substitute a 6 for x, and this is my notation just to keep my notes straight here. Let's go 6 plus 5, 6 minus 5, oops, oh, I'm sorry, that's a 1. Make that a 1. So let's see, so I got 11 times a 5. I got 55 there. Let's see if I get the same thing over here. 6 squared plus 4 times 6 minus 5. 36 plus 24 minus 5. Oh my garage, let's see. That's 60 minus 5, 55. Holy smokes, we got the same thing. So let me change colors here, and we'll do another one. Let's try, you know what? Let's make our life a little bit easier, and let's pick friendlier numbers that are easier to evaluate in our head. So I'll go 0 plus 5. I'll go 0 minus 1. 5 times a negative 1. I got negative 5 there. 0 squared plus 4 times 0 minus 5. 0 plus 0. Oh my gosh, this is why 0 is my favorite number in the world. Check. So far, so good. We've proven that there's two different numbers that are equivalent. Let's see if I can spice it up with one more new color here. Let's try x equals 1. That's a pretty friendly number. So I've got 1 plus 5. I've got 1 minus 1. 6 times 0 is 0. Woo, all right. Okay, let's try 1 squared plus 4 times 1 minus 5. 1 plus 4 minus 5. 5. Oh boy, I got 0 again. Bingo. So we're going to say that those two expressions up here are equivalent. All right. So these two expressions, they are equivalent. And just because for today we've picked 3 different values and they generated the same answer every time. All right, this next statement's really going to blow your mind. Any value that can be substituted for x and produce an answer of 0 is called a, wait for it, 0. Yeah, talk about blowing your mind, right? So anyway, we're going to practice identifying whether a value is a 0 or not. And their question is x equals 4 a 0 for this quadratic expression right here? So I'm going to go ahead, and it's as simple as substituting a 4, and we're simply wondering, do I get an answer of 0? So I got a 16. Whoops. Hopefully you caught that. Yeah, you're probably screaming at your computer right now saying, no, that's supposed to be a 4. All right, let's see. 16 minus 24 is going to give me -8. And then if I add those together, I get a 0. So I would say, yes, x equals 4 is a 0. Now they also asked me, how about x equals -4? So let's start all over really quick here. And I'll try substituting a -4 and see if that's also a 0. It seems like it should be, right? If positive 4 worked, it seems like -4 should work as well. That's positive 16 plus 24. Just be careful of your signs. A negative times a negative is a positive in both of those cases. 16 plus 24 is going to give me 40. 40 plus 8 is 48. So in this case, -4 was not considered a 0. Now, down the road, we're going to talk about the word 0 could also mean root or an x-intercept for that parabola, but we'll cross that bridge at a later time. So nice job hanging in there tonight, guys, and we'll catch you for another big day tomorrow.